What? Welcome to another Vlogging with Vlog. This is our kind of last, here's how to do something video. I'm gonna try and make one more for us, but really all that we have left for this class is kind of learning this last skill and then the quiz that will be up pretty quick. So if you wanted to kind of bust this class out and get done, you could totally do that, but otherwise it's on the schedule slated for Thursday. So we talked about how Ernest Rutherford discovered that radiation was essentially composed of three different things: an alpha particle, a beta particle, and gamma radiation. And in nuclear decay, that's when an atom just kind of shoots those particles straight out of the nucleus. Rutherford, so he did the gold foil experiment. He did that radiation and lead block experiment. He also figured out what we refer to as transmutation, or here's how we make new elements. And he did this in 1919. So he's kind of like a okay. He's like the dude in chem, really, for coming up with a lot of things that we really use today. He figured out that if you take something small and you get it going really fast and you slam it into something big, you can kind of get them to fuse together, and then we shoot off kind of little pieces. So this is the basis for how all of the rest of the elements on the periodic table were discovered. So anything above uranium was done using this process. The biggest particle accelerator that we have is located in Switzerland, and it's at the facility that we refer to as CERN, which is like the Center for Nuclear Research, something really sciencey. But it's crazy. A bunch of countries went in and tried to pay to create this thing just for research purposes. This blue tube is what I had shown up here before, and they have it surrounded by tons and tons of magnets, and around those magnets is liquid helium to keep them cool, to keep them from overheating, and they get these particles to go super fast, and then they slam them into each other to kind of come up with new particles. They call that bombardment. So transmutation and bombardment is the same type of thing. It's literally just causing a collision where you take something small and hit it into something heavy. Anyway, possible particles that you can get going around that track really fast. Just to review, we've got that alpha particle, which we symbolize with He42. That beta particle was just the electron, E-1. Gamma was the 0. Other ones that we might see are proton. So you'll see people write a lowercase p. And remember that that top number is the mass number, and that's the protons and the neutrons added together. So if you've got one proton and no neutrons, it would have a mass number of 1. And the atomic number is the number of protons, so it would have an atomic number of 1. A neutron we symbolize with a lowercase n, because capital N was already taken up by nitrogen. It would have an atomic number of 0 because there's no protons in it, and we give it a mass number of 1. And you can also see, oops, if I can scroll up, an electron, which is the same thing as a beta particle. So I just want to be really clear that we'd see kind of those pieces in a bombardment reaction. So if we tried one, this will look a little different than the decay reaction we did before, but the idea is completely the same. I will always tell you most of the pieces, and then we'll just have to figure out kind of what's missing, what's formed. We are taking cobalt-60. So the symbol for cobalt is Co, and that 60, that's the mass number. So I'm going to write that as the superscript on the left-hand side. And cobalt, you're going to need a periodic table for this, is number 27 on the periodic table. Do you see how it says plus a neutron? If you were going to do this reaction, you'd send that neutron around that particle accelerator really fast, so it would actually react with a neutron, and that was the symbol that I had written on the slide before. Okay, so this looks different than the decay reaction. If you remember, in the decay reaction, we started with one thing, and then it broke apart to make two things. So I'm going to do the arrow. So now it looks like we're taking two things and we're reacting together. So it says that we're going to form a new element and then we're going to give off an alpha particle as well. So I want you to picture anytime like two cars slam into each other, there's always like little pieces of glass and metal that get thrown, and that idea is the same anytime you slam two atoms into each other. There's always little ejected particles that get shot out as well. So we know that one of those particles is an alpha particle, so I'm writing the symbol for it, He42. I got to figure out what's missing here. The idea is the same as what we did in those decay reactions. The masses are conserved. So on both sides of the reaction, you should have the same masses. So over here, if I look at the reactant side, I've got a mass of 60 and a mass of 1. So total I have 61. Over here, I should also have a mass of 61. Oh my God, I don't have a calculator. What is that, 57? I think, killing it. Okay. Over here, the atomic number is 27 plus 0. I can do that as 27. 27 minus 2 is 25. So you're going to look at the periodic table. Number 25 is the element manganese. So this is how we can make that isotope of manganese. Let's do one more. Plutonium. So Pu. First, maybe read it. It says that it can be produced by hitting uranium with an alpha particle. So plutonium is going to be over here because we're making it. And its mass number is 239. And you'd look at the periodic table and see that plutonium is number 94. We're making other stuff. But in order to make it, we're taking uranium, 238. Oh, my phone is ringing, sorry. Okay, so 238, uranium is number 92, and I am hitting it with an alpha particle. So I'm gonna write He42. And it says some neutrons are released. So really what we're solving for is how many neutrons are being released. So I'm gonna write this guy, the symbol for a neutron is this. Here I've got 238 plus 4. So 242 is what that top part adds up to. I need the same thing. I have 239 here, so I need to figure out how many neutrons I need to give me a mass of 242 up top. I need 3 more, or a total of 3. You can write the 3 in front, or you could just write 3 symbols for the neutron total. But yeah, you're just kind of filling in the missing pieces. In class, we would have spent a lot of time kind of talking about how nuclear weapons work, because this is how they work. They take 2 pieces of uranium, and literally at the end of one of those weapons, if I switch colors here, kind of your basic nuclear weapon, it's like the barrel of a gun. They shoot 1 piece of uranium at another piece. And that collision not only forms kind of some new elements in there, but it also produces a whole ton of energy. And that energy is so great that so much devastation is able to come from that. But really I know in class we might have brought it up a few times, but the actual design for a nuclear weapon is very basic. I believe that the bomb that they dropped in Hiroshima, they hadn't even tested that style. They just kind of knew it would work. So yeah, it's crazy. You can do a lot of research. I know there's places on like the CDC, not the CDC, do I have it listed? FEMA, sorry, where you can go and see like what size bomb, what would that do to a city if you're bored and want to get kind of creeped out and look at that. But you guys, nuclear bombardment, try the practice problems, and then your quiz on Thursday is just on radioactive decay and nuclear bombardment, and then you did chemistry.